Justin, are you doing that calculation? Okay, we got body weight. Said 0.176. Okay. Okay, and that's the long way of doing it, right? So because you could have used sort of the 1-1 ratio, you could have used C1, D1, C2, D2. That would work under these circumstances. In this case, because it's a 1-1, yeah. Had it not been a 1-to-1 ratio, you would have to go with the long way. Because you have to take into consideration the molar, the stoichiometric ratio. Yes, yes. This would be the safest way of doing it. Or you'd have to use your C1, D1, and you have to take into account your stoichiometric ratio. Does that make sense? Everybody get that? I was hoping Mauricio would be here. Okay, questions? No questions? Okay, good. Okay, gravimetric analysis. So gravimetric analysis, it's not any different than what we're doing. It's the same concept. You're basically using your chemical equation to kind of get you guys started. But the fact is that you're going to make a precipitate. And you're using that precipitate to sit there and you're going to collect it. So you're going to use a funnel, you're getting gravity, and you're going to collect it. You guys have made coffee before. Okay. So in the case of coffee, we want the coffee, right? We don't want the coffee grinds. And so we're basically using a filter to collect the solid. So it's the same concept. Only thing here, now we're going to do a chemical reaction, and then we're going to recover. Okay. So this is just basically showing us that, you know, if we form a precipitant, we can collect what we've gotten by using a filter. Okay, here's your question. It says a 0.4550 gram solid mixture containing magnesium sulfate is dissolved in water and treated with excess of barium nitrate, resulting in a precipitation of 0.6168 grams of barium sulfate. This is our chemical equation. We want to check to make sure it's balanced. What is the concentration mass percent of magnesium sulfate in the mixture? Okay, what am I gonna do? You can tell it's a month. You guys are kind of zombies. Start with my given. Okay, so we have a couple of givens. So we have 0.4550 grams of solid mixture containing magnesium sulfate. And we also have 6168 grams of barium sulfate. Which given do I want to start? let's kind of picture what's going on. I always like to draw pictures. Now, sometimes it's not clear to me, by reading it out. So what's that going on? Okay, we're going to use that one first. Sure. Okay, so let's think about this, right? So first off, we know that there's a chemical reaction going on. They were nice enough to give us what it is. Normally, I wouldn't give you this, right? Exam, I'm not going to give you that. You're going to figure that out, right? So let's read it so that we can make sure that we understand what's going on. It says if we have a 0.455 grams solid mixture containing magnesium sulfate. So it's magnesium sulfate, it could be sand, it could be dirt, it could be whatever it is, right? Something else. So, but you only have so much of it that is actually magnesium sulfate. And the goal is to try to figure out how much of it is magnesium sulfate, right? So this is a whole bunch of gunk that's in there, right? We do this all the time, right? You guys have done experiments with a whole bunch of gunk and got something out? Yeah, just adding. Okay, we got this clay and we're going to add it in there and we get something to happen, right? Okay, so that's going to be dissolved in water and then it's going to be treated with excess barium nitrate. Now, the barium nitrate, its job is to basically isolate the sulfate. Okay, that's all it's getting rid of, is the sulfate. Okay, so all of the magnesium sulfate that was able to be dissolved in that solution, we should know how much it is, right? And that's the goal. By using that sulfate, we can figure out how much magnesium sulfate we had at the very beginning. Okay, so if we look at it, this is our gunk that has that magnesium sulfate. So then we add solution of barium sulfate, barium nitrate, nitrate, which we know is aqueous. Now barium, when it gets with sulfate, it forms a solid. How do I know that? Because it tells me that, for one thing. And also, if I didn't know that, I could also look where? On my chart, my little table, right? So then I know that I'm able to sit there and get barium sulfate. So I know I got barium sulfate out of that solution. Okay, so if I start with my barium sulfate, I can use that to figure out how much magnesium sulfate I initially started off with. Does that make sense? Okay, so 0.6168 grams of barium sulfate. Okay, so what am I going to do next? The molar mass. So I need the molar mass of barium sulfate. Where can I find the molar mass of barium sulfate? On the periodic table. So we have how many bariums? One barium. Barium weighs 137.33. Is that correct? I'm just pulling stuff out of my butt right now. So. Is that true? Yeah. Okay. Sulfur. How many sulfurs do we have? How many sulfurs do we have? Barium sulfate. Are you sure? Look at barium sulfate. Don't listen to what people say. Look next to it. You tell me, how many do we have? One, right? So you look what's next to it. There's one sulfur. Okay, so how much does sulfur weigh? Okay. And oxygen. How many oxygens do I have? 4. I have 4 oxygens. And we know that oxygen weighs, say 16, because I'm being lazy today. 16 times 4, because it's 15.99996. Is that 64? So that's 64 plus 32.06 plus 137.33. Add that all together. 233.39. That's grams per mole. Okay. So 233.39 grams over 1 mole. That's barium sulfate. Okay, so then that allows us to get our moles of barium sulfate. Okay, what else do I need to do? So if I have moles of barium sulfate, I can use what now? I can use the ratio, the stoichiometric ratio. What is the stoichiometric ratio of barium sulfate to magnesium sulfate? 1:1, right? So 1 mole of barium sulfate to 1 mole of magnesium sulfate. Okay, so now I got moles of magnesium sulfate. How am I going to get to grams of magnesium sulfate? The molar mass of fire. So, how many magnesiums do we have? We have 1. Magnesium weighs 24.305. And we have 1 sulfur, which we know weighs 32.06, and oxygen, which we know weighs 4 oxygens. So, 16 times 4. Okay, you guys get the same thing, 119. So we have 1 mole.
Oh, replace the 0 to 6.
What was that?
So replace the 0 to 6.
Oh, sorry. Thank you. Okay, who's doing that heavy lifting? Does it smell weird in here? It does. What does it smell like to you guys? Oh, gassy. That it smells like a marshmallow to you?
Like the marshmallow
The marshmallow float?
float? You know, like
Oh, when it gets burnt?
the cream.
Oh.
Like the cream.
Oh.
Oh.
Okay.
Oh, I see what you're saying. You guys, do you mind cranking it back to work? Yeah, I know you guys are gonna freeze. She, of course, wears her holiest pants on the coldest day.
I got like 39, 31, 80,
All right, 39,
31,
31,
80.
80. And that's grams. Okay, so magnesium sulfate. Okay, so then if we want the percent mass, then that's just gonna be that 0.3181 grams of magnesium sulfate over 0.4550 grams of our solid mixture. And multiply times 9. Okay, what do you guys get? It is definitely a Monday. You guys are looking 69.9.
0.69.
69.9%, right? See, it's about a fourth. Okay, it's about a third, yeah. Okay. Questions? Now you're cold. Sorry. You can get over here and get real warm. You know it should be warmer here. I like to keep it should be really chill. 68, 70-ish. Questions? Okay. Oh, sure. Sorry. I'll pull this for you. Yeah, poor Victor. He's not getting to see anything right now. Wall, maybe.
Yep.
Did I take the bread? I didn't eat it because I heard you weren't supposed to eat it.
Well, you can eat it afterwards.
Oh, really?
Yeah.
I didn't know that.
They had it with hot chocolate.
Oh, I was tempted. Okay. Combustion analysis. Kevin, don't fall asleep on me. Bored? Bored? No, just tired. What are you guys doing on this weekend? What did y'all turn up? You're like, we partied the whole week long, right? We had Halloween on Monday and then you're like, we had that exam and we're just gonna party the rest of the week. I can see Kevin just turn it up. Okay, so combustion analysis, we kind of talked about that before, right? We know we have talked about it. You don't remember it, we talked about it all the time. Did we talk about respiration, cellular respiration, getting ready to go on Thanksgiving? Right, you guys don't remember that?
Yeah.
You don't remember?
Now that.
Okay, let me help you guys. Okay, a combustion reaction is just a process of using a hydrocarbon or a organic compound being burnt, right? So let me give you an example. I'm sure we talked about it.
That's right.
Okay, so how many of you guys breathe? Anybody breathe? You breathe? Are you sure? Right? Okay, so what do we breathe in?
Oxygen.
We breathe in oxygen. What do we breathe out? Carbon dioxide. Our breathing in oxygen and breathing out carbon dioxide is an example of a combustion reaction. Our body basically is burning, right? Burning that food that we eat. So our ideal form of food is glucose. C6H12O6, that's glucose. So how many of you guys during Thanksgiving pig out? Right? Well, you throw it out, right? So you have everything, you put that plate on and you're like, you go, right? Do you guys do that, or is it just me? Right? You have to take that deep breath while you're eating and everything, right? Your head starts sweating a little bit, right? Okay, so. So what's happening at a cellular level? This is called cellular respiration. Why do you think it's called cellular respiration? What is respiration? Breathing, right? So we think of breathing. Cells are breathing. Well, why do you think they breathe? Come on, you're a bio major. You should know this. I haven't taken bio in a while. Anybody take bio in this class? Took bio. Anybody owning up to taking bio other than? Okay, so.
I had bio in high school.
Yeah, perfect. Yeah, bio has to use a bio, right? How many guys are anatomy or all that falls under bio, you know? You're in a health field, or right? You should know this, right? Why do you breathe? What is the purpose? And don't tell me to live, right? That's the big picture. I want the little picture. So that what?
Homeostasis.
You breathe for homeostasis. No, you do not breathe for homeostasis. Okay?
Resources.
Resources. What do you mean by that?
We need oxygen to use up the sugar that we eat, but that produces carbon dioxide. We don't want that building up in our system, so we need to get rid of it somehow.
Okay,
And
okay,
because they both naturally occur as gases, it's easiest to breathe it in and out.
okay. You guys are getting close. You're getting close. I'll kind of get you. Just kind of hitting onto that next topic that we're going to be talking about here anyway, right? Which is called thermochemistry, right? Okay, so let's talk about it. So you guys are getting ballpark close. I mean, really ballpark close. So she had broken it down that basically we need oxygen to break down the food that we eat, right? That's what oxygen is really for. So what's happening is that we have chemicals that we eat, right? Call it food, right? Those chemicals have bonds. Those bonds store, guess what do you think it stores? What's that? Energy, right? It stores energy. So what we do is we break down those bonds to get that energy. That energy is used to make ATP. You guys know what ATP is? Yeah, I know that's specifically what it is. But what is it used for? What is it?
It's power cells.
It is to power our cells. It's to power everything in our body, right? So ATP is used as our power source. It's the cellular power source, right? So we basically make tons and tons of ATP. With one sugar molecule, you should be able to make anywhere from 32 to 36 ATP, depending on how you count it. Okay? So that's from one sugar source, right? That little piece of sugar should make that much ATP, which is pretty damn good if you think about it, right? Now, I'm telling you the side, but I'll get that later. Now, the other thing is that for us in chemistry, the way that we associate energy or heat is by, whoops, the way that we associate energy is by what? By heat. It's like giving you the answers, right? So the way that we associate energy is by heat. So that's the reason why you guys are going to learn a little bit about thermal chemistry. So we associate energy with heat, thermal energy. Okay, those bonds, breaking up those bonds, releases that thermal energy, as well as it allows us to sit there and power up to make that ATP. Right. So that's what get from breathing in that oxygen. The man, the myth. Okay. It's all right.
A little.
We'll talk because I need to give a little bit of a presentation because you got some stuff to talk about with these guys. Set up those times, right? Okay, so this is a balanced chemical equation. How do I balance it? There's 6 carbons. So how many do I need to put? Let's put our show. So we have 6, 6, 12, and 8. Okay, so over here we have 13 oxygens. Currently have 2 hydrogens. So I need to put a 6 here?
Yeah.
Okay, 6 there. So that would be a total of 18.
A 9 of the oxygen.
A what?
A 9.
A 9?
No, because I'm.
Wait, hold on, make sure I count it right. That's 6 plus 12 is 18, right? So if I put a 3 in front of the sugar, what happens? Change my carbon.
So maybe put
Yeah, put it there.
Oh, what about a 6, right?
Yeah.
So 6,
12 and 6.
12 plus 6, isn't that 18? Okay. Boy, you guys, it's been a while, huh? Rusty. Y'all definitely turned up this last week. Okay, so this is an example of a combustion reaction. Like I said, we get heat out of it at the end of the day. But we also want to take a look at it. All of the carbon is coming from where? Where is it coming from? The sugar, right? All of the hydrogen is coming from where? The sugar, right? Okay, so both cases, it's all coming from the sugar. So we can use this concept in determining when something is being combusted, what that chemical structure is. Because what we're putting in is that oxygen. Okay? So you guys have done this. I know you've done this because we've done it before. Okay, you guys ready? So if I have, let's say, said generic hydrocarbon, we can sit there and always determine the chemical formula or the empirical formula based upon a combustion reaction. Okay. So the way a combustion reaction works is we put in excess amounts of oxygen. We put in our sample. This is our sample in this furnace, and we heat it up. And we heat it up. And so during that process, what ends up happening is that we get carbon dioxide, we get water, and then we'll get any oxygen that's excess, and we may get other gases depending on on what that chemical or that substance is, right? So we can end up with nitrogen monoxide or nitrogen dioxide or something along those lines, right? So at the end of the day, by looking at the amount of water that comes out, the amount of carbon dioxide that comes out, we're able to sit there and use that to determine the empirical formula. Okay, so here's a problem. It says polyethylene is a hydrocarbon polymer used to produce food storage bags and many other flexible plastic items. A combustion analysis of 0.00126 grams sample of polyethylene yields 0.00394 grams of carbon dioxide and 0.00161 grams of water. What is the empirical formula of polyethylene? So the way that we would go about this, since we know that all the carbon is coming from, it's going to be in the carbon dioxide. So we're going to start off with there. 0.00394 grams of carbon dioxide. You guys remember any of this? So what is the molar mass? Is that what we want to get to? Molar mass of carbon dioxide? How many carbons do we have? We have one carbon. How many oxygens do we have? We have two. 2 times 16 is 32 plus 12, that would be 44. 44 grams of CO2, 1 mole of CO2. Now, how many moles of carbon are in 1 mole of carbon dioxide? 1, right? Because it's a 1 carbon dioxide, 1. Okay, so 1 mole of carbon dioxide will give us 1 mole of carbon. Okay, we do that math. Sorry to take your spot. And then a spot for stuff. Is your card working?
You just open.
So anybody do the heart math for me? $8.95 times 10 to the negative 5. Okay, so then if we look at water, what do we have? 0.00161 grams of H2O. So we know that water weighs 18 grams per mole. How many moles of hydrogen are in water? Okay, do that heavy lifting.
Seven, 8 times 10 to the negative 4.
Now, since we're looking at the empirical formula, all we want to do is do a relationship between those two numbers. We want to take the one who has the smallest value and divide both of them by that number. So which one is smaller, carbon or hydrogen? Sure.
Oh, wait.
Oh.
That's right. Okay, so. Divide this by itself, we know that that's gonna be. That's gonna be 1C. Divide this one by. That's gonna be. You guys get it?
Times 10 to the negative
1.99 times 10 to the what?
negative 10.
-10? Are you sure? I put money on that? Don't forget to put this in parentheses. Yeah, 1.99.
No.
So you gotta remember to put that whole thing in parentheses because if when you enter it, right, then what you're doing is that you're dividing by this number, but then you're multiplying it by this number. But whole thing in parentheses. You get 1.99, but not 10 to the
No,
negative.
1.98
Yeah.
to the negative 10. So as it's supposed to be one.
It should be 1. No, not put the whole thing, put the bottom. in parentheses.
Oh, okay.
1.98. Okay, 1.98. Okay, so if you have a value of 9, right? Then you can round. We're going to round to the nearest whole number, 2, right? So then that means that our empirical formula is going to be C1H2. Okay? Understand. Okay. Now, so let's talk about when you don't get that. Right? If you don't get a perfect number that is 0.9 or greater, right? 0.9999. You know, those are perfect numbers, right? Let's say you get 0.8, 0.75, okay? So those guys, okay? So if you end with 0.2, so what can I multiply 0.2 by to get a whole number?
All right, you're like-
By 5? Okay. That's gonna be 1, right? What about 0.33? I skipped it, sorry. This is not cheap. 0.25 by 4. 0.33. 0.5. 3. I'm sorry. 0.66. 0.667. That's the same thing as 2/3. What kind of multiply 2/3 by to get a whole number? 3. 0.75. That's the same thing as 3/4. 4. 0.8. Okay, so if it's anywhere from 0.2 to 0.8, right? And from 0.2 to 0.8, you just need to sit there and get it. So, but once you multiply one of those numbers by that, you have to multiply the whole thing. So let's say, for instance, let's say we did the math and this ended up turning out to be, this is just for kicks and giggles, right? Okay. Let's say it turned out to be 1.33 hydrogens, right? And then we had 1 carbon. Okay, so if it's 1.33 hydrogens, what am I going to multiply that number by? Right. We'll multiply this one by 3, and we have to do the same thing to this. So then we end up with C3H4 times what? 5, sorry. 3 times 3 times 1, so no, that's
Dr. Henry, the 1.99 was like 1.98, would you still round it?
so.
As long as it's the
only-
number after the decimal?
That's right. So we want to look at that number. Yes, if that's a 9, right? Then we round it. If it's less than a 1, if it's 1 or less, you know, then you round it. But if it's 2, then these fools. Okay, does that make sense? Okay. Questions, concerns, catch? Okay, so this is just showing you how to do that. They end up with the same ratios. Okay, so can we take a little bit of a break? You guys mind? I gotta go potty, you know, I've been holding it for a while, so. Okay, so potty break, so I'll see you guys back here in 15. You can go to Mesa if it's open. Parts of it, so. Oh, it's gonna be decked out right now. By the time you guys finish next semester. It's gonna be long. We're gonna teach over there. Okay, so today we're not gonna do lab. I hope you guys are not disappointed, but I'll make it up to you guys. We'll do a kick-ass lab on Wednesday. Yes. Plus, you guys will be building your Formula 1 cars. So.
I saw that this Wednesday lab 8, but you said you were getting students.
I am.
Okay.
So. Okay. Yes, and you know, we're in that last stages of the class. So really, so what I want you guys to be thinking about, a lot of it is, so you guys are gonna use part of your lab time to build your Formula 1 cars. The other part of it, you guys are gonna come in here and we're gonna do some heat experiments.
Also, do you know when we'll be updating the grade book to the slide?
I will do that. I'll try
Just
to
so we
get that
know,
done.
you know, because we're
Yeah.
towards the end.
This weekend I will. If you turn in your most of your labs, right? The only thing that a lot of times I'll have you guys do unknowns, but most of the time you've already asked me what you guys have done what you're supposed to do with your labs, and then fill them out completely, you're gonna get full credit, right? Your homeworks, you know what you got in your homework, so that's one of the things that's the reason I have that, so it grades it on its own. And then your exams, I have to adjust them so they're in the right spot, so that'll adjust it. So if you know what you've done in your exams and on your homework, you pretty much have a really good idea. You turn in all your labs, you're gonna pretty much get full credit. Only ones that you always have to worry about are the ones that are the formal reports. Yeah, so those are the ones that I kind of take liberty on. I'll read over them and kind of rip them apart and stuff like that. But if you've done what you're supposed to do, you follow the instructions, it'll kind of be things, test scores, right? You know how to deal with the test. If you're not doing too hot on the test, you want to start doing the test corrections. So you can turn in your test corrections at any point. I'm being very lenient this semester. So if you did do too hot on one of your tests, then I'll do that. On Wednesday, I'll be handing out your last exam. That's going to be a take-home exam. And yeah, take-home exam. My take-home exams are always Saturdays, just so you know. Yes. So that's gonna be your last test, all right? So this is how it works with your take-home exam. So your take-home exam, you guys will have the ability to work in groups. And as long as you mention everybody who's in your group, right? They have to be mentioned in their take-home exam. You can talk to the TAs, right? You can use TAs. The TAs can help you, but they can't give you the answers. They're not gonna work it out. They're gonna just kind of down. But you are able to use your textbook, you're able to use yeah, it is. But it's gonna take some time to think about it, right? And so a lot of the stuff that you're learning today, stuff that you guys learned just a few minutes ago, that's gonna be what the bulk of the exam is. And of course, there's some other things in there that I know. So it's gonna account for the fact that by next week, I should be covering this part, right? And if I don't, then you guys will get that one as a free question, right? So, okay. Okay, questions?
So like, that's our last test?
That will be your last test except for the final.
Oh,
Yeah, so
so
you
we
still have the
technically have
final.
two.
Yeah, so technically you have two.
Okay.
And the final's all multiple guess.
Yes.
And the way the final works is it's gonna cover a certain parts of things. Certain things we're not gonna cover in this class, they're actually part of next semester, right? And then any of those questions that you happen, and I may give you like a little cheat sheet to kind of help you through it, because I typically will print out some things. Anything that you happen to get right on those ones that we did quote cover in this class, you will get, they will add as extra credit points to your score. They won't hurt you. Okay. But everything else that you've covered, you're expected to know. Okay. No, this one is, it's an ACS exam. So I've been working on for the last couple of years. It's one of the things I'm trying to build, as you guys can see, I'm trying to build a strong chemistry program, right? First off, got to get a damn grade. We're working on it. Hopefully, knock on wood, this semester might be my golden year. It would be so great if that happens, right? So after this, right, after we've done it at this point, then I'm planning to try to get funds for the program itself, kind of help sustain it and kind of, take some of the pressure off of the district so that we can sit there and support ourselves. So and that gives a lot more liberty to water, things like that. But to do that, I need to figure out how you guys are pairing against the nation. So we have you guys take this exam. It's called the ACS exam. ACS stands for American Chemical Society. They dictate chemical education, right? So this is what you need to know. This is what you're supposed to do. This is how you're supposed to do it, right? And then they kind of dictate everything across the nation, across the world, actually. And so that way, chemical education is kind of uniform. It's one of the places that is pretty uniform compared to all the other areas. And so I use that to kind of dictate how I teach the course and what is valuable. And plus, I was taking consideration what I've learned in what's going to be important, what I believe that you guys should know from coming from certain industries. Now, ACS has a lot of power. So we want to try to get their favor, right? So the idea is that the last couple of years we've been building this program every year. I see where you guys stand compared to other colleges and national, right? So that gives me means to ask for funds for certain things like, hey, we can improve this education by doing this. And so I can use your scores to sit there and validate those.
So you want us to make some,
No. I want you guys to listen. I don't want you to fail because that affects your grade, right? I want you guys to ace it because it also shows I get more money. Believe it or not, I would get more money if you guys show progress, right? If you guys are showing that you guys are doing really well, right? I get more money that way. Then if you guys are doing mediocre or poor, right? They say they give money for that, but it's not nowhere near as much money as they give for schools that are doing well, right? Then I can also implement a lot more programs, right? Things that are happening here because you guys are getting that good foundation, so there's not money wasted. And this is what people don't understand. If you're in a system that is doing poorly, right? People look at it as money wasted. They're just throwing money at the problem, right? Rather than getting solutions. If you're in a system that's doing well, it's easy to get money, right? People want to give. You think about it. Who give free stuff? Do poor people get free stuff? No, it's always the rich that get free. Oh, you want a free meal? You want a free car? Oh, we want you to sample this, right? They always get free stuff, right? And it's the same mentality that they do with funding in a lot of cases. If you're doing well, they want to give you money because it makes them look good by contributing to you, right? If you're doing poorly, they don't give you money because you've been doing poorly. You've probably been doing poorly yourself, you know? So that's how they look at it. So it's a lot easier to get money when you're doing well than it is when you're doing poorly. Okay. Okay, so let's talk about some heat. So we're going to start off with the energy basics, and then we got to work our way through. I think I went too far. Okay. So things that you should know about heat, right? So energy is involved in everything, right? We eat because we need energy, right? Digest, right? We just had that burger earlier, right? I just had those what are those cheesy thingies, right? I like it. So good, right? So at the end of the day, we're metabolizing food. We already talked about that process, right? The fact that we're breaking it down, carbon dioxide and water, and we're using that energy that's being released from the body. So that means that bonds, chemical bonds, can store energy. That's what it boils down to. So that's the reason why we use gasoline. We use gasoline for what? For energy, right? Right. So we basically use the bonds of those long carbon chains to sit there and provide energy to power our car so that we can get to where we want to go to, except if you're giving you a hard time. I'm sorry. Trying to make you laugh a little bit. Okay. So we also use it in the production of raw materials, right? Or from raw materials. So energy is going to be very valuable to us. So we need to kind of understand how it pertains to chemistry. Now, the way that we're going to be looking at energy is going to be a little bit different than other things, right? We're going to be looking at it as heat that's being absorbed or heat that's being released, right? So you guys remember absorption and kind of talk about absorption of energy. So if it's being brought in as endothermic versus exothermic. Endothermic. Okay, so if we're putting energy in, it's going to be endothermic. If energy is being released, okay, so I want you guys to really think about this, right? So if I'm standing next to a fire, that ball there that's burning, is that going to be endothermic or exothermic? Exothermic, because it's released. So me taking in that warmth, right? She wanted to take it in earlier when I had the door open. Notice it's closed now, right? She's like, close that damn door, right? So in that case, then what's happening? In that case, that standing next to that ball. You're going to be absorbing. Now, it's always going to be a perspective, right? Because from the log's perspective, it's exothermic. From your perspective, it's endothermic. So we always have to get reference to them. And so for us as chemists, we always try to make a reference by using that plus and minus sign. So if something is positive, we have a positive heat, right? Or what we'll call right? Then in that case, if it's a positive value for it, that basically means that you put energy into the system. And if it's a negative value for it, that means that you're taking energy out of the system. Okay? So I want you guys to start thinking along those lines. Now, this whole process of looking at those chemical and physical reactions or physical changes, that process is going to be called thermal. Oh, hot, man. It's hot. Okay, so let's start talking about what energy is. Energy is very simple. It is about doing work, right? So I keep telling you guys, are you guys putting energy in the classroom? Time to the classroom. Are you sleeping on me? Right? You're not sleeping on me, okay? So That process, right, is energy, the capacity to either supply heat or to do work. Now, we're going to expand on that process a little bit later as we start talking about gases and things like that. We'll brush on it in this chapter, but not too much. So there are two major types of energy. They fall into two major categories, and then we can break them down further from there. The two major types are potential and kinetic. Potential energy is basically energy associated with an object being in a relative position. Okay, so for instance, if I'm standing on top of a mountain or a hill, or in this case, a falls, a waterfall or something like that, and then I'm standing up there, right? So that has all potential energy. Now, that's just on position because it's height. Physics, you know this, right? Your real house. Okay, now as soon as I decide I'm gonna dive into the water, right, down those falls, which I would not do that, that's fucking crazy, right? So as soon as I decide to do that, it goes from potential to what? Kinetic, because there's motion going. So then we have kinetic energy. Now, potential energy is the highest at the point when I'm just standing up there at the top of the hill, right? Because that's the highest position I'm at. As soon as I jump off, I start changing my potential energy into kinetic energy. And then when I hit the water, that's when my kinetic energy is at its highest. It should be equal to that potential energy that I'm at. Okay, so it literally goes like this, right? One goes up, the other one goes down. Okay, so this brings us to a couple of things, right? There's this law that we talked about. We talked about it, and we talked about it, we talked about it, we keep talking about it. Right? What law do you guys think I'm thinking of? Law of conservation of energy, right? Because energy is conserved, right? All we're doing is going from one form of energy to another form of energy. That's what life is about. It's going from one form of energy to another form. Okay? It's always conserved. Keep it in mind all the time, right? So a lot of times we think, oh, energy is lost and energy. No, it's going somewhere, right? It's going to be counted somewhere. It may be going out in the fucking backyard instead of in your house, right? But it's going somewhere. Right? So have you guys ever, in the middle of winter or something like that, get your heat on and somebody had their window open or something like that? I'm wasting that energy. No, you're feeding the nature, right? You're helping nature get a little bit warmer there. Okay, so we know that energy is going to be conserved. Okay? Energy is always conserved. So bottom line, energy is never created, nor is it destroyed. It's just changed. And so we have to start thinking of our systems when we talk about energy, because we can sit there and limit our system so that things look like it's lost, but in reality, it is. Okay, so we have to think of it as a system. Okay, we'll talk more about that in a second. Now, this is thermochemistry, so we're going to talk about heat, right? We're going to be focusing primarily on. So thermal energy is a form of kinetic energy. Why is it a form of kinetic energy? What was that? Because there's motion. What else are we going to say? Movement. Okay, you guys are saying exactly the same. Because there's motion. Because if you think about a chemical, right? We know that chemicals are always moving except when? When are they not moving? When are they not moving, Kevin? What was that? Well, there is, you're right, when it's freezing, but there's a specific, if it's just zero, they're still moving. Not neutral. She's right, when she said, say it again.
Absolute zero.
Absolute zero. Absolute zero, right? So that's the significance of absolute zero. Things stop moving at absolute zero, right? And you guys need to keep that in mind, okay? You always want to keep that in mind. So as long as we're above absolute zero, we know that absolute zero is negative 273.15 degrees Celsius. Or we could just say 0 degrees Kelvin, right? So that is absolute zero. At absolute zero, nothing is moving, right? So you have no kinetic energy. So that means that you have no thermal energy, right? Okay. So long as it's above that, we're gonna have kinetic energy. We're also gonna have thermal energy associated. So we know that when things get colder, does kinetic energy speed up or slow down?
Slow down.
Slow down. Okay. And we know that because we've been on the beach where the sand was really hot. And we raced our ass to the water to cool off, right? Well, if the sand wasn't hot, you just kind of shimmy down, you work your way, trying to, this is my bathing suit, trying to show that body that you've been working on the whole summer, right? If the sand wasn't too hot. But if that sand is hot, you're racing your butt down, right? So that also kind of helps us remember that it's going to speed up, right? Things are going to speed up the hotter we get. The colder we get, things slow down. Now this isn't, it works a little bit, although this one is working much better than the other. Green. Balls under there. Okay, so these are two different types of thermometers, right? So this is our classic alcohol or mercury thermometer. How do you think they work? Since you guys know about molecules and things, and you guys just told me what happens when things heat up. They move faster, right? So if they're moving faster, they're probably going to take up more space, right?
Yeah.
So if we keep heating them up, eventually it turns out they go from solid or liquid into what? Gas, right? So then they'll be taking up more and more space as they heat up because they're moving faster. They're like, initially they're doing this, they're just doing this a little bit, and then as you heat them up, they're doing this, and then they're doing, popping off the wall and everything, right? So we know that's happening. So then, can you guys explain to me how a thermometer works?
There is a liquid at the bottom of the bowl. And the warmer that liquid is, the more it expands. And the
Okay.
thermometer itself.
So when you
measures.
say expand, is it expanding because there's more liquid getting in there?
It's expanding because of heat.
So that means it's expanding because of heat because of what?
The molecules are bumping into each other more and need more space to move around.
So they're moving more. Okay. So at the end of the day, it boils down to things are moving more. So at the end of the day, a thermometer works because shit moves, right? It moves more when it's hot. Okay. So that's basically how a thermometer basically works. Now we also have what we call a bimetallic thermometer. Another thermometer. These are often used as thermostats. Okay. So they're used to determine thermostats. So in the case of a bimetallic thermometer, we basically have two pieces of metal that are kind of pulled together. Why are you guys laughing? Both are giggling here. What's going on? What am I missing?
And you're making some fun about it. Now you're saying like when you boil down into.
Oh,
Yeah, we get your.
my dad jokes? Is that what it is? Okay. I didn't even recognize they did that. Well, look, I'm good. Yeah. She's getting all hotter. I'm hotter over here, right? See, I knew thermal chemistry has that effect on people. Okay, so we talked about these two metals, right? So when it's cold, what happens to those metals? When they're cold, what happens to them?
Condenses.
It condenses. So they come closer and closer together. It's cold. You warmed up, baby, right? And then as soon as they get hot, they're like, don't touch me. Spread away, right? Isn't that how it works? Okay. So because of that, you're able to sit there and use the fact that the room's getting hotter. And then so your thermostat says, oh shit, it's getting hot. Let's cool it down, right? So it cools it down and everything like that. And then when it gets cold, they get really close together. No, we need to heat back up. And then so it'll actually send signals because of that, right? I'll keep that in the case of the thermostat. Okay, so we're going to be talking about heat. Now, when we talk about heat, heat is going to be transferred. Heat is going to be transferred between two bodies, right? Think about this. Okay, you're laying in bed with your baby, right? Your boo, right? You don't lay in bed with your boo. Okay, no, okay. So you guys all sleep alone? Is that what you're telling me? Okay, so do you guys got the cold feet or do you got the warm feet? Cold feet? Oh, I hate you guys. Oh my God, right? So my ex-girlfriend, she used to always put her feet on my back, right? And so And it drove me crazy because her feet would be so damn cold, right? She was a popsicle. And then, so what happens? What happens in the case of her putting her cold ass feet on my back? But she was taking it, she was stealing all my warmth. So it was being endothermic, right? And so because she was stealing my warmth, what was happening to me? I was getting colder because her cold ass feet, right? So the thing is that what happens is that heat is being transferred between me and her, right? So as a result of that, we will reach a point of thermal equilibrium, right? Where we meet somewhere in the middle. She's happy because she's warmer. I'm pissed because I'm colder, right? Like, no, don't put your cold feet on me. Okay. So this process is called heat flow or heat transfer. There is a whole course that is dedicated to heat transfer. You guys are going to get a little bit of it. Understand it now. You'll ace that course. I guarantee. Okay, so the hot temperature is going to be basically flowing to the low temperature substance. And again, you're going to get to a point where you reach the same temperature, or what we call thermal equilibrium. Okay, so this is just basically showing us that, right? So I'm hot, she's cold, right? She's like, I'm hot, she's not. Okay, so then you put us together, right? We get to a point where all my heat is being transferred to her. Then we reach a point where we're balanced, thermal equilibrium. Okay. So you guys already know about exothermic and endothermic. We've already talked about it. So just remind me, exo meaning, is that going to be absorption of heat, or is that going to be release? Okay, so we know endothermic is that absorption of heat. Okay. So here's some examples of exothermic and endothermic. So if we have an oxyacetylene torch, right? So we use oxyacetylene torches to basically bridge metals. So do you guys think that's endothermic or exothermic? Okay. The rails that are there, is that going to be endothermic or exothermic? Okay. So how many of you guys run into walls? Get drunk and run into walls. I think we've all done that. Everybody's embarrassed. I tell them, we know what happened this weekend. She's getting all giggly now. She's telling the whole story now, right? So in that case, we know that she goes out and you get a little, worked up there, right? So here's a couple of things that we should know about alcohol. Does alcohol make you feel warmer?
Yes.
Yeah.
It actually does, right? Do you want to know why? Because you're actually breaking the bonds between the alcohol, right? So those carbon bonds, they store energy, they store that heat. So if you drink a lot of alcohol, you start sweating a little bit and getting all, and then especially when you drink way too much, believe me, I know you start praying to the porcelain gods and you're vomiting and everything because your body starts to process it all, right? So in that context, you're getting really, really hot. Now, after you drank way too much and you run into a couple of walls, you may need that cold pack, right? Because that head hurts after you hit it a couple of times. Believe me, I know. So in the case of a cold pack, what it is that you have water on the outside of the bag. On the inside of the bag, you have ammonium nitrate. Ammonium nitrate will actually take in all of the energy from the surrounding, from that water, break it open, sucks in all that energy, right? Then it gets cold. It goes cold, sucking in that energy. So endothermic reactions are going to feel cold. Exothermic reactions are going to feel hot. Log. Put your hand next to a log, it's hot. You put your hand on a log, is it burning? It's hot, right? Yes, that's right. Yes, exactly. Okay, so units for heat. So we're going to talk about units that we typically use in the US, then we'll talk about units that they use everywhere else. We always do that, or we'll call that SI. Okay, so in the US, we use calories. So a calorie is just the energy that's required to raise 1 gram of water 1 degree Celsius for a calorie. So you're just changing a single degree, right? 1 gram of water. You guys got that down, right? Okay. I said a calorie is the energy required to raise 1 gram of water 1 degree temperature of Kelvin or Celsius. Okay. Now, that's, we're going to say small c calorie. Okay? Small letter c calorie. Now, the large letter c calorie, I know this is crazy. This is what we do in the US, right? We give them the same name. Capital C calorie are basically food calories. A capital C calorie is going to be 1,000 small c calories, or a kilocalorie. Okay. Now, I don't know why we do that. We do that. Trying to figure out why. But when we talk about calories of food, that's capital C calorie, right? Which means it's 1,000 C calories, little c calories. I know, same name, crazy, crazy. Okay, so SI units for heat, work, and energy is going to be a joule. Okay. Now, joule was named after this guy named Prescott Joule, right? And so a joule is the amount of energy used when the force of 1 Newton moves an object 1 meter. Okay, so that would be a joule. Okay, so 1 calorie, 1 small c calorie is going to equal to 4.184 joules. Okay. So, a little math on the side here, rather than just. Oh man, it fixed my board. I don't have my. Break it again. Okay, so that means I can actually use the side here. So I guess I'll use the side. Oh, actually, it's dedicated to one. Okay. So, knowing what you guys know, so my Cheez-Its here, and I'm going to eat the whole bag, are 100 calories. Okay. Capital C calories. Oh, you guys can't. Okay, so my bag of Cheez-Its here are 100 calories. I want you guys to determine how many joules we have, and then also how many small c calories. So where am I going to start at? I give it. Okay, we have 100 calories. So what is the conversion from capital C calories to small c calories? 1,000. There you go. So we go 1 capital C calorie. So it's okay if I say cal, capital C cal. That's going to equal 1,000 little c cal. Okay, so. So if we have 100 little sea cows, how many joules is that going to be? So we know that the relationship between a joule and a calorie, for every 1 calorie, that's going to equal how many joules? Remember, we were talking about sig figs. One sig fig there, right? Zeros, since there's no decimal point there. Zeros aren't gonna be zero. Okay. Questions? Concerns? Cash? Piece of cake? Everybody got it? Okay. So if we have the heat capacity is going to be an extensive property. Okay, so in this case, if we think about, we have a small pan and we have a large pan. Right? So the heat capacity of the large pan is going to be greater than the small pan. Okay? And that makes sense, right? Because there's more to the large pan, so we can take more heat. Now, if we take a look at this equation, C here represents the heat capacity, capital C represents the heat capacity. Q represents the change, represents the heat, and delta T represents the change in temperature. Okay. So we get our equation. Nice. So then we can change our equation around. Q equals capital C delta T. Now the units for our heat capacity is just going to be joules per degrees Celsius or Kelvin. They're going to be comparable because the change in temperature is always going to be the same between Celsius and Kelvin. Now, specific heat. So specific heat basically means that we're taking out mass in this case. So in this case, if we're already taking the mass out, that's the reason why we have to multiply it by mass. The specific heat, this lowercase c, is going to be equal to my equation. Q is going to equal MK. I know, it's crazy, right? Where M here represents the mass, and now we're using a small c to represent the specific heat capacity. Now, specific heat capacity is an intensive property. Now, that basically means that it's not going to be dependent on the amount that you have. It's only going to be dependent on the substance that you have. Okay, so is it ice? Is it water? Is it iron? Is it wood? Is it? Okay. So, and again, we're going to be using that delta T. Delta T represents the change in temperature. Now, when we talk about that change in temperature, that's always going to be final minus initial. Now, because specific heat depends on the substance that we're using, we have all of these tables. I am not kidding. They're about, I have a book that's about this big of tables of different specific heats for different elements. So like you guys can see here, helium, it has a specific heat of 1.193, where iron has a specific heat of 0.449. Do I need to come and look? Yeah. Okay, let me get them to this one point, and then I'll come back. Okay, so the amount Q, since we have Q is going to be equal to C times mass times delta T. So if Q is going to be positive, then, or our heat is going to be positive, what do we know? I said if our heat is positive, what do we know is happening? Is that going to be endothermic or exothermic? If heat is positive, it's going to be endo, right? So in other words, the system is going to be gaining heat, or the substance is going to be gaining. Okay, so that basically means that our T final is going to be greater than our T initial. So if I have a cold piece of metal and I put heat into it, right? Is that cold piece of metal going to get hotter? Okay, if I have a pot on the pan, on the stove, right? Initially, I can touch that pot, right? Do I want to touch that pot after I put some energy into there?
No.
Why not? Because it got hotter, right? So that also shows us that we're putting heat into our system. So that's a positive value, right? Now, if I have a hot pan, and then I touch it later after I turned off that energy, let's put it in. That's going to have a negative Q value, right? Because we're losing thermal energy. So is it okay for me to touch it after it's been sitting there for like 3 hours or something like that? Because we know that it's cool, right?
If it's positive, that's endo.
If it's positive, it's endothermic. And then if it's negative, it's exothermic. So it's the same thing that we talked about at the very beginning, right? Okay, so here's your question. A flask containing 8.0 times 10 to the second grams of water is heated, and the temperature of the water is increased from 21 degrees Celsius to 85 degrees Celsius. How much heat did the water absorb? Okay, so I want you guys to contemplate that. You're going to use that table that you guys got for your heat capacity of water. Let's take a magnifying glass to see it. Thank you. Okay, we got some answers, right? Man, I can't use my board. Okay, so. What I always, for me personally, what I always like to do is, I like to write down what everything is. So we know that this is the mass, right? So that's gonna be my N. So what was small c? Okay, so small c is equal to 4.184. Oh, that sounds very familiar, doesn't it? And we know that that was joules per grams. In this case, Celsius. Okay. So then our delta T, we said it's going to be equal to final. So we have 85 minus 21. 64. So we have Q equals small delta T. So that's going to be equal to, you have more results from?
Essentially, it was on its own. It was that also. Yeah, that was clear.
But it's still like 50 times better than that. Yeah. And then we're not going to precipitate. Just gotta make it. I think we just gotta run it through the system. Is that thing the big?
Yes, sir.
Yeah, my guess, so my guess is that, remember how the one that you just cleaned with the water? So if you would probably compare to the other two. Right? Then I guess that there's remnants of stuff that wasn't totally pure in there. So we're gonna do a good job of flushing. So I think we just gotta fill it up again. Flush it out. Yeah. But it's deep. So trying to solve any problems. By the way, I need work studies. Does anybody need any extra cash that they would like to get from school? Work in the lab. Certain days of the week. So I need at least 2 work study students for next semester. They don't pay great. I'm not gonna lie to you and say they pay good, but you get to work with me. It's a lot of fun. What was that? And it looks really good. A lot of things. Okay, and then the delta T is 65, 64 degrees. Out of that advertising. Okay, what did you guys get for Q? That's good. How many sig figs do we have? Two sig figs. That is 8.0. So it's 2.1 times 10 to the fifth.
So, quick question, what are TF and TI supposed to stand for? Like, what do they mean?
Final
Final and.
emission.
Okay, thank you.
Okay. Preguntas?
See. What is like the difference between the capital C and the lowercase C? Because one is heat capacity, the other one's specific heat capacity.
So the difference between it is that capital C already has the mass incorporated. Lowercase c is independent of mass because you have to add. So that's also, if you look at it, that's why they call it intensive versus. Capital C already has mass incorporated in it. So then that way it's dependent, it's going to be dependent on mass, right? Where lowercase or amount, right? So let me go back.
So which one's extensive and which one's intensive?
Intensive is the lowercase c, and extensive is the capital C. So extensive basically means that it's going to be dependent on how much you have. And then intensive means that it's independent. Independent.
Dependent on what?
It's, in this case, it's independent on mass. Okay. So it's not dependent on how much it has. It's just dependent on what it is. Okay. So that's the reason why we have mass outside of it. Because you have to tell me how much you have. Okay, so here, these are solar panels. You guys seen the solar farm up there where there's like a little ocean and everything like that? And when I first drove by here, just got started, I'm like, there's water out there? You know, I really thought it. Anyway, so this is basically how solar panels are basically going to work in this case. But it's basically heat transfer. It's the concept of heat transfer. So they basically use a fluid. That fluid basically goes to a heat exchanger, and it exchanges heats based upon the solar panel. So sun comes in, heats it up, gets that all hot and bothered, right? So then that hot and bothered will cause steam to come down here. It causes that turbine to move. So then that turbine moves, creating that energy. We stored in a generator, and then we're able to sit there and make power. Right? At the same time, we recycle that energy, cool it off, and then come back here, put it back through the heat. And that process starts. Right? So it goes through here, it gets heated up, then it comes here and makes steam. And so this is a renewable energy, right? So, and that's one of the benefits of using solar panels because it's renewable energy, not losing. Unlike gasoline, where we actually have to cut those bonds to make carbon dioxide. Now, if we were very efficient at going back from carbon dioxide and making that back into gasoline, that would be perfect, right? Perfect case because everybody likes using gas. You know, how many people like cooking with gas? Cooking with gas. Yeah, rather than those little, or you know, you're like, yeah. I feel like I get nice, evenly cooked things where in the case of some of those metal coils, half of them work and the other half don't work, or the middle ones heat up more than the other ones, you know. Okay, so that brings us to I can't talk to it. Okay, kilometry. Okay, so basically kilometry is the art of measuring the amount of heat that's being transferred from one substance to another, right? It's just that heat exchange. So to do this, we use a very sophisticated instrument called the kilometer. Kilometer basically is going to allow us to do that measurement of the heat that's being exchanged from a system. And I'm exaggerating, it's not very sophisticated. I'll show you what it breaks down to. So here is a rudimentary kilometer. So this here basically represents our kilometer. You have a thermometer, you have water, and you have metal. So that metal there that's dropping in is going to be the heat, right? The thermometer is serving to as our measurement means of kilometry because it really can have a change in temperature, right? So the key about this is that we have to break it up in terms of our systems and our surroundings. So the surroundings here is going to represent the water that's surrounding it. The metal itself is going to be representing the system that we're actually looking at. That's going to that physical change. So in the case of kilometer, things are going to behave exactly the same way. So if something is exothermic, that basically means that heat is going to be released into our surroundings or into our solutions. If it's endothermic, that basically means that heat is going to be going into our system, right, from our surroundings. Here, case of an endothermic, so here's our system, and so you can see heat being released into our surroundings. Exothermic. So as a direct result of that, the temperature is going to come down. In the case of endothermic, our system is now going to be getting that heat. So our temperature is going to go down. Make sense? So kilometers can be very, very simple in construction. So the most commonly used kilometer is the coffee cup kilometer. So in the case of coffee cup kilometer, all we do is have a styrofoam cup. We have the lid and we have a thermometer. And we have something that we can stir. Okay. So this is an example. So here we have our thermometer, we have our stir, and then this represents the whole thing altogether. So again, we're just going to be using that change of temperature to sit there and determine what it is. We know our specific heat, we can look that up on the table. And so we're just looking at that change where the temperature starts and where the temperature ends. Now we can get fancy with the thermometer, right? So here, these are two. This is a simple, very inexpensive one. We actually have one around here somewhere. And here, again, we have our thermometer, we have our stir, and then we have a tube that's within another tube, right? So this inner part is going to be insulating. This is a support ring. You make sure that you're not losing any heat to the temperature, to the surroundings. This is your internal metal vesicle. This is your outer metal vesicle. Okay, so in the case of more expensive one, these guys are typically more accurate. They're often used in research and in labs. So I hope we get one day. I keep praying and begging, and maybe they'll break down and get me one. But so in this, we have a very precise thermometer. We have motorized stir, right? But the concept is exactly the same. You still have your support rating, you still have your internal metal vessel, and then you have your external metal vessel. So here we're going to be using a piece of metal and cool water. So M is going to represent metal, W is going to represent water. So we know that when we talk about a metal being dropped into water, a hot piece of metal being dropped into water, what's happening? The temperature will increase, right? So, and the temperature of the water will increase. What happens to the temperature of the metal? It what?
Would it decrease? Because it's like.
That's right. It's going to decrease until what happens? Until equilibrium. Okay. Okay. So now, how do we represent that in terms of energy not being lost? Right? So the way that we represent that in terms of there's no change in our energy, no net change in our energy, is Qm plus Qw equals 0. So at the end of the day, it has to add up to 0. The amount of heat that you're giving off from the metal has to equal the amount of heat that you're getting from the water. The only thing that's going to differ, that's going to change, is the sign. So when we say it, the heat of the metal is going to equal the heat minus the heat of the water. And that makes sense, right? Because it has to add up to 0. The change that occurs has to equal 0, right? Because of what? Observation. Okay, this is just showing us that, right? Okay, so we're going to go ahead and do the problem. What are we doing on time? 4 o'clock. We're doing pretty good on time, right? We're out at 5. Okay. So actually, let's go ahead and we'll take another little break. Let's say 5 minutes, 5-minute peak break, and then come back here. And then hope you can work away. Try to do the chat.
And was built around the most energy study. So she can take the higher you are. is by like showing off like their energy level through their windows. So the color that they have in them is what how powerful they are. Basically. I'm not sure where exactly within those. Maybe on the islands.
The one that, right,
Maybe patterns. Certain patterns that are like other ones.
Just But you can check the one.
So the person that are not will still have like. Basically like the base. The undertone of their color.
It's just a network.
And some parts of the like tone, like the head, like. Face and shoulders. And then they'd have the bright color windows.
yeah.
Okay. Yep.
Again, going back to the capital.
And
So you know how large you see, like, we know what it looks like.
Also,
Big
there's one
jewels,
there.
jewels, or
Yeah, the
what would it be for the, like,
they have the
Capital
same
C.
stuff.
So capital C is just gonna be jewels,
Yeah, the mouth.
jewels
The
for
mouth and the iris.
degrees Celsius or
And then
degrees,
some are just more.
or degrees, they're gonna be the same.
On the
Because
inner
we're looking at the change in
elbow
temperature.
and palms.
So it doesn't
because they'll be,
matter,
like shorter
degrees
than
Celsius or degrees.
Right.
They can't really be anywhere that's hidden. Because I'll be drawing out.
Yeah, for pattern. Possible pattern.
Yes. Okay, guys ready to start on this one? So. Now that we're gonna be using U equals. C delta T. I like to call it MCAT. That's easy for me. Looks like MCAT. How do I know I'm going to use that? First off, because what's given to me, right? So I have a piece of metal that I'm allowed to get the mass, right? Then I also have my water, which I know is going to be given to me. And we're going from a temperature change of 24 degrees all the way up to 42. They also told me that I'm going to be using my specific heat. And then I'm looking at heat transfer. So in other words, I'm looking at Q of the metal has to equal minus Q water. Okay, so just the fact that we're talking about a change in temperature, right, that immediately should trigger something about us using always the heat. And they also want us to calculate. So we know that in the case of Q metal, that's going to equal the mass of the metal, the specific heat of our metal, and then the change in temperature of the metal, right, which is going to be the T final minus T initial. Okay. We know that the T final for the metal is going to be 42.7. Okay, because it says the final temperature of the water is measured to be 42.7. So use gateway, isn't it? So we know the metal weighs 360 rebarbs, or 360 grams. Rebarb weighs 360 grams. So we'll have to look up the specific heat of metal. We said it's iron, it's rebarb of iron, so that's 0.449. The units were joules. Said that we know the final was 42.7. Obviously, we're looking for T initial, right? Okay, so then for our Q water, so Q water, that's going to equal less. That's going to equal the mass of the water. Okay, so now if we think about the mass of the water, C so then in this case, W. Okay. So what do we know about water? What is the density of water? And what is the significance of density? Why am I even going to do that? What are the units of density? Density equals mass over volume. So that means this is ways that we can change mass to volume or volume to mass, right? So we know that the density of water is always going to be constant. So water is always going to be equal. If you want to be precise, you can look it up. If I can spell right. Let's see. IMIS. The density of water is 1 grams per milliliter. Okay, so if I have 425 milliliters, how many grams would that equal?
Can you repeat that?
If the density of water is 1, and if I have 425 milliliters, how many grams would that be? Yes. How many? 425, right? Because it's a 1-to-1 ratio, right? 1 gram to 1 milliliter, right? So so I can just go ahead and use that. So the heat capacity is multiplied is 4.184. That's joules per degrees Celsius. You guys mind if I move this? Like I'm just teasing you. Mess up everything, so you can use your big board and then you gotta fix it so they can't use it anymore. Joules, grams, Celsius. Then we're gonna multiply that times that temperature, which is the final temperature is 42.7 minus 24. 0. I had a question. What's the question? I'm hearing things. Maybe I did have a good time last night. As a photo, I stack some of these figures on it. Yeah, that's fine. You guys get the same answer? Probably not because,
I have something else.
yeah. How about this number?
So be it.
3.32. Oh, yeah, right. That's the sig bigs, right?
Yeah.
Okay, so 3.33 times 10 to the fourth joules. Okay, so then we're gonna plug this into this equation here. We're gonna plug this into that equation there. And right above where everything else is been. 60. You guys can't see. Let me see if I can find it. Do you mind if I erase this part here? Got this already down.
Yes.
And what two is this guy. It's right here. And we're gonna have equal to its value. Okay, so now what we want to do is solve for TI. Got a question? Oh, minus.
Q F again negative.
Good job. I was just testing you out there. So if I take these numbers, divide them up by both sides. 42. 7. Equal 3.3 times joules divided by 60. Four, 5. Grams. C. running out of room real quick. I apologize. So then I get my TI. Is gonna equal. So our negative, I'm gonna count it here. So versus. 10 to the 4. Over 60. 4. Plus. Good question. Why did I change to a negative from a positive? Because, yeah, I rearranged the whole equation. So technically, I'm subtracting this on both sides, the 42.7. So that would be minus 42.7 over here. So then I have a negative in front of my temperature. So then if I divide everything by -1, that makes this positive and that makes that positive. So you get 249 degrees Celsius. Now, the thing about these problems, they're not hard, they're just tedious. They're long. And then, you know, the whole thing about the signs. I'm notorious for screwing up on signs, right? So you want to pay attention to your signs. Yeah, that would be smart. Okay. Questions? Concerns? Yes. Because 24 is our midpoint, right? So you're thinking about your final temperature, the temperature where they kept it equilibrium. Yeah, so they're both. So the metal is dropping down to 42, and the water is releasing up to 42. Yeah, that's right. So you're trying to calculate. So we calculate the metal. Okay, how's everyone else? You guys doing okay? Okay, good. Everybody got it down? Dave did pass out. So I love giving questions like this, although I like to make it a little hard. So, okay, so when we talk about colorimetric principles, so this process, what we just talked about with the metal, also can work with reactions as well. So if we're trying to determine the heat of a reaction, if we know that heated solution then we can calculate that reaction because it has to be equal to each other. Right? So the heat of the reaction for the heat of the solution is going to equal 0, or we can say Q reaction is equal to Q solution. Okay. Okay, so this will be the last thing, and then we'll stop here and pick this back up on Wednesday. Okay, so it says when 50.0 milliliters of a 1.00 molar HCl and 50.0 milliliters of 1.00 molar of sodium hydroxide, both at 22.0 degrees Celsius, are added to a coffee cup thermometer. The temperature of the mixture reaches a maximum of 28.9 degrees Celsius. What is the approximate amount of heat produced by this reaction? Your first instinct would be, yes, that makes stoichiometry. But reality, no. Okay. So you want me to show you how you're going to do it? Okay, so we have a volume that is primarily mostly water, 50 mils. We have another volume that is primarily mostly water, another 50 mils. So that is a total of 100 mils of primarily water. So what do I know about the density of water? 1:1 ratio. So that basically means that we have 100 grams of water. Okay, so if I have 100 grams of water, I can basically use Q equals impact water. So we have 100, actually 100.0, right? And then we know it's 4.184. That's grams. Oops, sorry, joules. Joules per gram Celsius. And then our change of temperature was 28.9 minus 20. So then our Q water equal okay. So we also know that Q water is going to equal minus Q of reaction. So then Q of our reaction R is going to equal negative 890 joules. Okay, So does that mean it's an endothermic reaction or it's an exothermic reaction? What was that? Endothermic reaction or exothermic reaction? Exo, because it's a negative value. Okay, piece of cake. So the tricky part was recognizing that you didn't have to do all that work. I remember our instructor gave us, I mean, it was a bitch of a problem. There was multiple parts. And you're like, oh, I went through and I did all of the molar calculations and everything like that. And I literally, like, I spent so much time on it. And then I found out it was just this. I was so mad. I was just like, okay, so we'll stop here. We'll pick this back up on Wednesday. The plan is